Formation of diamond deposits, from mantle to surface. Diamonds are among the most remarkable minerals on Earth, formed under conditions that exist far below the planet's surface. Their story begins deep within the Earth's mantle, typically at depths of 140 to 200 kilometers, where temperatures reach around 1,200 degrees Celsius and pressures exceed 45 kilobars. Under these extreme conditions, carbon atoms crystallize into a tightly bonded cubic lattice, giving diamonds their extraordinary hardness and optical brilliance. The source of this carbon can vary. It may come from primitive mantle carbon, preserved since the Earth's early history, or from subducted oceanic crust, which introduces carbon back into the mantle through tectonic processes. Over millions of years, these carbon atoms slowly transform into diamond crystals, remaining stable only within a narrow field of pressure and temperature known as the diamond stability zone. However, diamonds cannot remain buried forever. Their journey to the surface depends on rare and powerful volcanic eruptions. These eruptions originate from deep mantle regions and travel upward at astonishing speeds, carrying with them molten rock known as Kimberlite or Lamproite magma. Unlike ordinary magmas, these are volatile-rich and extremely rapid, rising through the crust in a matter of hours. As they ascend, they tear off pieces of the mantle, known as xenoliths, some of which contain diamonds that formed millions or even billions of years earlier. When the eruption reaches the surface, it creates a pipe-shaped volcanic structure, commonly referred to as a kimberlite pipe. Over geological time, erosion exposes these pipes, allowing the contained diamonds to be released and transported by rivers and streams. This process can give rise to secondary or placer deposits, where diamonds accumulate in riverbeds, coastal sands, or alluvial plains. Thus, the formation of diamond deposits represents a complete geologic cycle, a story that begins in the depths of the Earth's mantle and ends at the surface, where humans eventually discover and extract these ancient gems. Each diamond carries within it a record of the deep Earth's history, revealing information about the planet's composition, thermal evolution, and the dynamic forces that continue to shape it. Types and distribution of diamond-bearing rocks. Diamonds are not evenly scattered throughout the Earth's crust. Instead, they are hosted by specific rock types that originate from great depths and serve as natural carriers of these precious crystals to the surface. The two principal host rocks for primary diamond deposits are Kimberlite and Lamproite, both of which are ultramafic volcanic rocks rich in volatile components such as carbon dioxide and water. Their chemistry and eruptive behavior are uniquely suited to transporting diamonds from the mantle without destroying them. Kimberlite is by far the most significant and well-studied diamond-bearing rock. It typically occurs as vertical, pipe-shaped intrusions that penetrate through older continental crust, particularly ancient cratonic regions that have remained stable for billions of years. These regions provide the ideal thermal and pressure conditions for diamond stability. Kimberlites are rich in magnesium, iron, and potassium, and they often contain mantle-derived xenoliths, fragments of peridotite and eclogite that reveal the deep origin of these magmas. Most of the world's commercial diamonds come from kimberlite pipes, such as those found in South Africa, Botswana, Russia, and Canada. Lamproite, though less common, represents another important diamond host. It differs from kimberlite in both chemistry and texture, being richer in potassium and containing unusual minerals such as leucite, sonidine, and phlogopite. Some of the most famous lamproite deposits include the Argyle mine in Western Australia, which produced a large portion of the world's pink diamonds, and deposits in India and the United States. Lamproites form under conditions similar to kimberlites but may originate from slightly different mantle sources, possibly enriched by ancient subduction events. Beyond these primary deposits, diamonds can also occur in secondary or placer deposits, formed through the erosion of kimberlite or lamproite pipes. Over time, weathering and surface processes release diamonds from their host rocks, allowing rivers and streams to carry them downstream. Because of their extreme hardness and chemical resistance, diamonds can survive long-distance transport and accumulate in alluvial gravels, coastal beaches, and even marine terraces. Many historical diamond discoveries, such as those along the Orange River in South Africa and the Kasai region of the Congo Basin, originated from these secondary sources. The global distribution of diamond-bearing rocks reflects the deep structure of our planet. Most economically viable deposits occur within or near ancient continental shields, such as the Kopval, Africa, Siberian, Russia, Slave, Canada, and São Francisco, Brazil, cratons. These stable tectonic blocks preserve the cool, thick lithospheric mantle necessary for diamond formation and survival. By contrast, young tectonic regions, where the mantle is hotter and thinner, rarely host diamonds. In summary, the types and distribution of diamond-bearing rocks are controlled by a combination of deep mantle processes, ancient tectonic stability, and surface erosion. From kimberlite and lamproite pipes rooted in the cratonic mantle to secondary deposits scattered across ancient river systems, each occurrence tells a story of the Earth's geological evolution and the long journey of diamonds from their hidden birthplace to the surface. Exploration and mining of diamond deposits. The discovery and extraction of diamond deposits represent one of the most fascinating and technologically advanced aspects of economic geology. Because diamonds occur in very specific geological environments, exploration requires a deep understanding of both surface indicators and subsurface processes that guide geologists toward potential sources. From identifying favorable cratonic terrains to advanced geophysical surveys and large-scale mining operations, every stage of the process reveals the intricate connection between Earth's deep mantle and human ingenuity. The exploration of diamonds usually begins with regional-scale studies, aimed at locating ancient and stable continental blocks known as cratons, since these are the primary hosts for kimberlite and lamproite magmatism. Within these regions, geologists look for subtle signs of past volcanic activity, such as circular topographic depressions, magnetic anomalies, or indicator minerals that point to the presence of diamond-bearing pipes. Among these minerals, garnet, ilmenite, chromite, and clinopyroxene are particularly significant. They occur as resistant fragments released from weathered kimberlites and can be transported by rivers or wind for great distances. By sampling sediments and soils and analyzing the chemistry of these indicator minerals, geologists can trace their source areas upstream, often leading to the discovery of hidden kimberlite or lamproite bodies. Once a promising target is located, geophysical techniques such as magnetic, electromagnetic, and gravity surveys are employed to map the subsurface structures in detail. Kimberlite pipes, for example, typically produce distinctive circular magnetic signatures due to their iron-rich mineral composition. Drilling programs then confirm the presence and quality of the rock, followed by microdiamond analysis, which estimates the potential diamond grade and economic viability of the deposit. If exploration results are favorable, the focus shifts toward mining operations. Diamond mining can take several forms, depending on the type of deposit and its location. Open-pit mining is the most common method for extracting near-surface kimberlite pipes. It involves removing large quantities of overburden to reach the ore, which is then transported for processing. In deeper deposits, underground mining techniques such as block caving or sublevel retreat are used to extract the kimberlite at greater depths. For secondary or alluvial deposits, placer mining methods are employed, ranging from small-scale artisanal panning to large industrial dredging operations along river channels or coastal plains. The processing stage is equally crucial. The mine material is crushed and screened to liberate the diamonds from the host rock. Because diamonds are extremely dense and hydrophobic, separation techniques such as dense media separation, grease tables, and X-ray fluorescence sorting are used to isolate them efficiently. Each recovered diamond is then cleaned, weighed, and graded based on the 4CS, carat, color, clarity, and cut potential. Modern diamond exploration and mining also emphasize environmental sustainability and ethical sourcing. The extraction of diamonds has long been associated with environmental disturbance and social issues in certain regions. To address this, international initiatives such as the Kimberley Process Certification Scheme have been established to prevent the trade of conflict diamonds and promote responsible mining practices. In addition, reclamation and rehabilitation of mined areas are now standard requirements in most jurisdictions, aiming to restore landscapes and ecosystems affected by extraction activities. Ultimately, the exploration and mining of diamond deposits combine some of the most advanced methods in geology, physics, chemistry, and engineering. From tracing microscopic mineral grains in river sediments to designing massive underground mines, every step reflects centuries of accumulated scientific knowledge. Each diamond recovered is not merely a gemstone, it is a fragment of Earth's deep interior, brought to light through the union of natural processes and human determination.